This is the new unit. This is 7-1, scatter plots and lines of best fit. Here's example 1. A local football team has gained the following yardage in its first 7 games. And it says graph the data. Make sure anytime you graph that you have the information, and so you have to have a title. So we're going to call this football yards. Gonna have to label my x-axis and my y-axis. So my dependent variable is yards. My independent variable is game. That's because x is always your independent and y is your dependent. Okay, and then you're going to have to do your increments. So I'm going to go by 50s, 50, 100, 150, 200, 250, 300, and then this is 0, and 1, 2, 3, 4, 5, 6, and now I'm going to go ahead and graph it. And so 1 is 348, 1 is, there's 350, so about right there. 2 is 350, right on the line. 3 is 300, again right on the line. 4 is 295. 5 is 280. 6 is 250. And 7 is 225. And so what this is called a scatter plot. And sorry that my copy is a little bit different. My my printer doesn't like PDF sometimes. The above graph is called a scatter plot. Scatter plots are an excellent way to model real-life data to observe patterns and trends. We use scatter plots to help us see if a correlation or relationship exists between the set of data. And so what I'm going to look at is I'm going to say, as the games increase, the yardage decreased. Can you identify a pattern in the above data? Yes. The number of yards decrease with every game. Most of the time, real world data doesn't fit into a nice straight line, so it's not, they didn't decrease the same amount every game. We are going to draw a line of best fit. It's found to make predictions. This line is drawn so that the points are evenly distributed and below the line, above the line and below the line, and seem to cluster around the line. So sometimes you'll have outliers, which means they don't really fit that well. And so if I draw a line that looks like, I didn't do a very good job with that. Let me do it again. Doing a line of best fit. I didn't do a very good job. Here, let me show you another one that looks a little bit better. There's a line of best fit where the plots, and see some are above and some are below, and that's called a line of best fit. It's made to do predictions. So then once you have your line of best fit, you should be looking at this where you're now going to ignore the plots and you're going to extend the line. And so I'm going to take a sheet of paper and I'm going to extend the line, because it's going to make a prediction on game 10, and here's game 10, and I read across and it would be 160. So after you do a scatter plot, You draw a line of best fit. From the line of best fit is where you make your predictions. There are 7 possible types of correlations, and they are this. So there's a perfect correlation. That's your line. That means everybody acted exactly the same from all of them. There's a strong positive correlation, which means when I draw my line of best fit, the data is clustered around the line of best fit. There's a weak positive correlation, which means if I draw my line of best fit, the data is farther away from the line of best fit. There is no correlation. Looks like somebody spilled pepper on my paper. That's no correlation. I cannot make any predictions. Here is a weak negative, so I would do my line of best fit, and the data points are far away from the line of best fit. Here is a strong negative correlation, which means my data points are close to my line of best fit. And then perfect negative means everybody's acting the same way but is a negative. What type of correlation did the data in example 1 have? It was a strong negative. And here's a second one. Sorry for having to do a couple of papers at a time. Here's example 2. Old Faithful is a geyser in Yellowstone National Park. For more than 100 years, Old Faithful has erupted every day at intervals of less than 2 hours. The data in the table may suggest that the line between the eruptions may be related to the length of the previous eruption. Make a scatter plot and draw in the line of best fit. So one of the tasks that you will be asked to do during this unit is take some data, plot it onto a graph, making sure that all the components of your graph are there, and then explain what kind of correlation. So what are we graphing? We're graphing Old Faithful eruptions. We have length of eruptions. Time is almost always your x-axis. So this is length of eruptions, and I can tell that it's in minutes. And then time until next eruption. And that is also in minutes. And then I need to scale, and I'm going to do 10, 20, 30, 40, 50, 60. I'm going by tens. And I'm going by half a minute because I am seeing that my data is falling in between minutes. And you can make your intervals different. So one axis can go by tens while the other one goes by halves. That's fine as long as you're consistent. So I have 2 at 57. And 2.5 at 62. And 3 at 68. And 3.5 at 75. Kind of already see that they're going, it's trending up. 4 at 83. 4.5 at 89. And 5 at 92. And I'm going to do my line of best fit. I'm going to take a straight edge and see if I can do a line of best fit. Or some are above and some are below. Got that one a little bit better. And then I'm going to ask what kind of correlation, and remember it's one of the 7. Well, since the data points are very close to that, it's going to be the line of best fit. It's strong. and it is going into a positive, so it's a strong positive correlation. And then once I have the line of best fit, then that means I can make predictions, and I ignore where my data points are, and then I go off the line. Based on your line, if the length of the eruption was 1 minute, so I'm going to continue out my line. Continue my line out. I'm going to go from the 1. I'm going to hit the line, come across, and it would be 38 minutes until the next one. Okay, make sure that your prediction is a logical number. So then we get into, a lot of people get happy about going, okay, I'm going to graph a whole bunch of stuff, and when I graph a whole bunch of stuff, I am going to say, hey, it's positive, but there's a caution. Correlation does not necessarily mean causation. So what that means is just because there's a strong correlation between data does not necessarily mean that one data is causing the effect is occurring in the other set of data. So you're going to have to ask yourself, does that have anything to do with the other thing? Like, does the independent have anything to do with the independent? So we're going to look at some examples. We can see that there is a correlation, also called an association, between the sets of data, but is there a causation? So here is an example of a causal relationship and its graph. Hours of study and a test score. So it does predict that the more you study, that the higher your test score is going to be. Hours of studying is causing higher test scores. Yes, I know some of you will say, oh, I don't study and I still get high test scores. I understand that. But for the most part, the more people study, the higher their test scores are. Here's an example that shows an association. So here's an association, but not a causation. And so we're talking about jars of strawberry jam sold in New York, and then number of CDs sold in Florida. Does the number of strawberry jam have anything to do with number of the CDs sold in Florida? And it does not. And so that is where there is an association, but not a causation. What your assignment is going to be is to plot some data points, create a line of best fit, explain whether it is what kind of correlation there is.